Hello, class. So on this video, we'll start on section 3.6 in the book. So this is section 3.6. So chapter 3, section 6. Now, before I start, let me summarize what we did in the previous video. So in the previous video, we talked about the superposition principle. And then more importantly for this section, we mentioned that the method of undetermined coefficients really only works when the function on the right-hand side of the ODE, right, which we call g of x, is a combination, which means either a sum, difference, or product of polynomials, exponentials, and cosine and sine functions. Why? Because these functions either repeat or go to zero when we are taking derivatives. And since in our particular solution, we have to include all possible terms that come from all possible derivatives, if those derivatives eventually don't go to zero or repeat, then we have a problem. We're going to have infinitely many terms to include in our particular solution, and we can't solve a system of equations with infinitely many unknown variables. So as I mentioned, we're going to try to generalize this method that we're talking about so that we can do it where g of x is not necessarily a combination of polynomials, exponentials, or sine and cosines. Okay? So that's what we're going to do in this section, and we're going to call this section variation of parameters, and you'll see why we give it this name. Okay. So definition 1: given a second order linear ODE, and remember that since it's second order, right, we can always divide by whatever is multiplying y double prime, right? And we get something of this form, right? Y double prime plus p of x y prime plus q of xy equals g of x. This is the form of a differential equation we're going to work with. Now, notice that I'm not requiring the coefficients to be constant, right? P of x and q of x could be expressions involving x. That's going to be fine. Right? Everything that we're going to do here is going to work in the more general case where the coefficients are not necessarily constant. Right? For our purposes, we're mostly only going to use it when the coefficients are constants, but if it works more generally, why not just derive the formula more generally? Okay. So first, I'm going to give you this definition. So given a differential equation like this, we call it the general solution to the homogeneous case, right, where when g of x equals 0. Right, we call that the complementary solution of the ODE. And we're going to denote it y sub c. Right? So I'm giving it a name so I don't have to keep saying the solution to the homogeneous case. I'm just going to say the complementary solution. Right? And immediately you should know, okay, he's talking about the general solution for the homogeneous case when that is when we make g of x equal to 0. Okay? So that's the only definition we're going to need. From now on, we're just going to go ahead and derive a method to find the general solution of this differential equation. Okay? So again, consider the second order linear ODE. And again, we're not requiring the coefficients to be constants, right? Notice that p of x and q of x could be expressions involving x. The only thing we're going to require is that, oh, what is this here? Oh, that's weird. The only thing we're going to require is that p of x, q of x, and g of x are continuous on some interval I. That's going to be the only requirement we're going to have. And from this, we can go ahead and derive the method. Okay, so first, suppose that y sub c, the complementary solution, suppose that we know it, right? So suppose that we know the complementary solution, y sub c, is c1 y1 plus c2 y2 on some interval I. Now, there is something I need to note here. Theorem 1 from section 3.5, remember, that's a theorem that was saying that in order to find the general solution in the non-homogeneous case, you find the complementary solution and a particular solution and add them. That theorem, even though I stated it in the form in which our second order ODE had constant coefficients, it actually works even if the coefficients are not constant. And so that's what I'm saying in this note here in orange. Right? So theorem 1 extends to any ODE that looks like star. Any second order ODE, as long as it's linear, doesn't have to have constant coefficients, meaning that in order to find the general solution, it's still the same process. We find the complementary solution, right, the solution to the homogeneous case, right? And again, it's second order ODE, so we're going to need two solutions, right? So because that's the fundamental set of solutions, and then we have to find a particular solution that satisfies this original ODE. Okay? So keep that as a note, right? It's important that theorem 1 extends to any second order linear ODE, not necessarily having constant coefficients. And what I wrote in purple is basically what follows, right? That means that the process to find the general solution, right, for this ODE is, as before, to find the complementary solution and find a particular solution. Add them together, and that's going to be the general solution to the ODE. Okay, so now that we know that's the process, well, what we're going to do is, so notice that we already assumed that we know what the complementary solution is. Right? So in the case that the coefficients of this differential equation are constants, we know how to find the complementary solution, right? In the case that they're not constants, we don't know how to do that. So I'm just going to assume that we are given the complementary solution. Right? So we know what the solution for the homogeneous case is, what the general solution is. Right? So that's given to us. If it's not given, then that means that the coefficients are constant and we can find the complementary solution ourselves, okay? So the only thing that's left is to find what the particular solution is, because again, we're assuming that we're given the complementary solution, right? So what we're gonna do is we have to derive a method to find the particular solution, just like we did in the method of undetermined coefficients, right? So we will assume that y sub p has a particular form. We're going to assume that y sub p has the form u1 of x times y1 plus u2 of x times y2, where u1 and u2 are to be determined. And y1 and y2, of course, come from the complementary solution, right? From the same y1 as y2 here. So actually, let me write that here so it's not confusing. Y1 and y2 come from the complementary solution, which is denoted y sub c. Now, why does it make sense for us to try to work or find a particular solution of this form? Well, the idea is we kind of want to mimic what we did in the method of undetermined coefficients, right? In the method of undetermined coefficients, we would have something that looks like some function, right, times an unknown constant plus some function times an unknown constant, right? And depending on how many terms g of x had, how many terms came out from the derivative of g of x, that's how many constants with terms we would have in our particular solution, right? Now, in this case, we want to use the information we have, right? The only information we have as of now is what the complementary solution is. So it makes sense to try to look for something that is not a linear combination because they're not constants, but some sort of thing like this, where you have something times y1 plus something times y2. And again, this kind of makes sense because it's the only information we have. All we know is what y1 and y2 are. Now, we can't use constants for u1 and u2 because if we did, right, we would be in the general solution for the homogeneous case, and y sub p would go to 0. So since we can't use constants, well, we replace constants with unknown functions of x, right? As long as these are unknown functions of x, y sub p is not gonna be in the solution to the homogeneous case. Meaning that when we plug this into the ODE, this is not gonna go to 0, right? And it'll be possible, potentially, for us to find what u1 and u2 have to be in order for y sub p to be a solution, right? So that's where this reasoning comes from, right? We're using the information we have, y1 and y2, and we want to be able to vary, right, some parameters here. And in this case, the parameters are not constants. Again, they're functions of x, in this case, u1 and u2, so that when we plug this into the ODE, y sub p doesn't go to 0, right? And that is why this method is called the variation of parameters method, because we're hopefully going to vary u1 and u2 in a way that we actually get a solution, a particular solution to the ODE. Okay, so hopefully that explains why we would try to work with a particular solution of this form. Again, this doesn't come out of nowhere. There's always a reasoning why we try what we're trying. And that's what I'm trying to show you, right? Because again, in the future, you might end up trying to solve differential equations, whether they're all ordinary differential equations or partial differential equations. And it might be possible to get an exact solution instead of using approximations, right? So this is an example of something you could try, right? or the reasoning, right? It's an example of something you could try if you're trying to get an exact solution instead of approximating. And again, that's very useful. Right? Now, as always, what we're going to do is we're going to plug in y sub p in this form that we have into the ODE, right? Set it equal to the right-hand side and see what we get. See if there's a way for us to determine what U1 and U2 have to be in order for y sub p to be a particular solution. Okay, so let's see what happens when we plug in y sub p. Now, it's going to be a lot of work, so I basically typeset it beforehand and just copied it here, right, so that we can just go faster, right? Because really, all we're doing is plugging this in and combining terms in a convenient way. So nothing else is going on right now, right? So that's why I'm just going to show you what I did and not do it, from scratch, because I don't think it's too illuminating. Okay, so it's a second order ODE, right? So we're going to need to find the first derivative of y sub p and the second derivative. Right? So I found them, and we're gonna have to use the product rule because we have products of functions of x, but you can do this, right? It's just calc1. Now I'm going to plug it into my ODE, right? So what's on the left-hand side is the original ODE, right? So y double prime plus p of x y prime plus q of x y. Right? So again, all I'm doing is I'm going to plug this in. Right? So I plug this in, and I'm going to be combining terms in a very convenient way. Right? So after I plug it in, I'm going to be combining my terms like this. I'm going to factor out AU1 to get this term here. I'm going to factor AU2 to get this factor here. Sorry, not term, factor. Now, why did I do this? Remember that by assumption, y1 and y2, right, they come from the general solution of the homogeneous case. Remember what that means. That means that both of these terms go to 0, right? Because this is the original differential equation. We plug in y1 and y2. Since they're solutions of the homogeneous case, by definition, these things have to go to 0, right? So that simplifies, and we get the second line. Right, so now we're on this line. Okay. Now, what am I going to do here? Again, I'm just doing some rearranging, like noticing that some things are derivatives of other things, right? Until eventually I get to this last line. Right? So again, you can read over that to figure out what I did. Again, nothing crazy, just combining terms in a nice way. And if something is a derivative of something, I'm writing it like that. So for example, in the line above, I have something that looks like y2 times the derivative of u2 prime, right? So a derivative of that product, right? So I just write it like that. Right? Again, nothing enlightening going on, just simplifying as much as I can. Right? So eventually I get to this last line. Okay? Now, unfortunately, in this last line, there's nothing much else I can do to simplify. I simplified as much as I can. But I still want to simplify this because remember, my goal is to find what U1 and U2 are. And with what I have here, I simply don't have enough information to find what U1 and U2 is. It's still very general. So if we're doing this for the first time, right? Or think of this as we're doing this for the first time, we're trying to derive this method on our own. What is something that we can do now? What would be a next step if we're stuck at this particular spot? So what is that other thing that we can do? Well, one thing that would be nice, and just one thing, just one possible approach, it's going to turn out to be the right approach, but I'm going to explain why you would do something like this, like always. Notice that this term here and this term here are the same, right? One is the derivative of the other, right? One is inside the prime, the other one is just multiplying p. If those two things were 0, that would be nice, right? Because that would simplify my equation. I would just be left with this part. So if you're stuck, one really nice thing that you can always do, remember, you're the one in control here. You're not restricted by almost anything in what you try, right? So if you're ever stuck, what's something you can do? Add more assumptions to your problem. Right? And this is a technique that works in anything, in any mathematical course, in any engineering course. Anytime you're trying to solve something like this, you're in control. So just, and anytime you're stuck, you usually get more information from, well, having more assumptions, right? So of course, if you add more assumptions, you're kind of restricting what the solutions can be. But what's better, to not have any solutions or have solutions that are restricted by assumptions? Well, it's better if you have solutions that are restricted by assumptions than not having any solutions. Right? So that's the idea, and this is something you can always improve. Maybe there are assumptions that are not as restrictive that still give you solutions, right? So that's the sort of thinking you want to have. If you're ever stuck, you're in control, you can add more assumptions. That's going to restrict your solutions. But again, having no solutions, having restricted solutions is better than having no solutions. Okay, so that's what we're going to do. What is the assumption that we're going to add? Okay. Again, it'd be nice if those things disappear. So I'm just going to make them disappear. I'm just going to assume that that expression is equal to 0. So let's see, let me do it in green. Assume furthermore, so another assumption. Remember, we already have the assumptions that of the form of yp, right, that it's a product of u1, y1 plus u2, y2. And we also have the assumptions that p, q, and g are continuous, right? So we're adding another assumption to that, right? So it's on some interval, right? So assume furthermore that that expression is 0. So y1, u1 prime plus u2, y2 prime equals 0. Then our ODE simplifies. Right? If we do this, then as we mentioned, this goes to 0, this goes to 0. So what are we left with? Well, we're left with y1 prime, y1 prime u1 prime plus y2 prime u2 prime equals g of x. Now you might think, well, I mean, I still don't know how to solve for u1 and u2, right? However, if we combine this with the assumption above, right? So I'm just going to include this assumption here. I'm going to write it below it. So this I'm going to write right underneath. Right? So this is y1 u1 prime plus y2 u2 prime equals 0. Now notice what we have here. This is actually a system of two equations in two unknowns. Why? Well, what are the two unknowns? Well, the two unknowns are u1 prime and u2 prime. Right? y1 and y2, they're given to us, so we know what they are. y1 prime and y2 prime we can also find because we know what y1 and y2 are. So really, what we have here is two equations in two unknowns. And again, that's good, mimicking what we were doing in the previous sections. Whenever you have n equations, and generally in n unknowns, there's a chance you can actually find what those unknowns are. Right, so that's the idea here. So I'm going to write it here. Note, this is a system of two equations in two unknowns. Did I misspell that? Yes, I misspelled it. In two unknowns. So there's a chance for us to solve it. Now, the method we're going to use to solve this system, and I mean, you can use other methods. Like you could solve for u1 prime in one equation, plug it into the other. However, I'm going to use another method just because if I use this other method, the solutions just look a little bit nicer, and they kind of work with things that we've used in the past, and you'll see how that works. Right? So again, you can solve it by hand, but the way we're going to do this in this class is we're going to use something called Cramer's rule. Now, I won't explain what Cramer's rule is. However, it's a useful tool. Computationally, I don't know how efficient it is. There are things that are more efficient for sure. But in certain situations, it's nice because the solutions have a really nice form. And that's the form I want to take advantage of. So this is something that you would find in any linear algebra book. Or if you just Google Cramer's rule for solving systems of equations, then you'll get what this is, right? For our purposes, it doesn't really matter how it works, right? What matters is that we can use it to solve this system, and we can solve for the unknowns. Right? We can solve for u1 prime and u2 prime. Now, the solutions that we get are these after using Cramer's rule. So let's do it in, let's do it in black. If we use Cramer's rule, we're going to get that u1 prime equals negative y2 times g of x over w. And I'm going to explain what w is in a moment. And u2 prime equals y1 times g of x divided by w. Now, what is w? W is going to be this determinant. It's going to be the determinant of, well, y1, y1 prime, y2, y2 prime. If you notice, this is just the Wronskian of y1 and y2. So this is why I wanted to use Cramer's rule, because we can write the solutions in terms of something that we know how to compute, right, easily, just Cramer's rule. So it looks nice, right? It's a simplified version. Again, you could solve this by hand, but you maybe would not realize that what's in the denominator is just the Wronskian of y1 and y2. Now, why else is this important that we're writing it like this with the Wronskian? Well, we know we're dividing by w here. What happens if w is 0, right? That could be a problem. However, we know it's not 0 on the interval I. Remember that this is the general solution, right? The complementary solution works in some interval I. Now, since y1 and y2 are a fundamental set of solutions, they're linearly independent. On I, they're linearly independent on I. Remember, that means that the Wronskian is not equal to 0 on I. Which implies this is not equal to 0 on I. So we're good. We're not dividing by 0. So these are the solutions, because, well, now we have y1 prime, y2 prime. Just integrate to get u1 and u2 and write down your final solution. So which implies integrate to find u1 and u2, which implies you can find yp, right? Or let me write it like this. Now we know what yp is exactly, right? This is u1, y1 plus u2, y2. And the general solution of the whole ODE is, well, oops, that doesn't look like a y at all. This is y equals the complementary solution plus the particular solution. On what interval? Well, on I. Remember, I was the interval. So we need some things here. I is the common interval where, let me see. So actually, let me give it another name. Let me give it I. So let's say on I2, where I2 is the common interval, because there's a couple of things we have to look for. It's a common interval where YC is the complementary solution, right? We had an interval coming from there. And we also needed P, Q, and G to be continuous. Oops. So P of X, Q of X, and G of X are continuous. Right, so look at those two intervals, make sure that the interval works for both of these, and then that's the interval where it works. And we're done. Now, oh, actually, why did I square the whole thing? So let me focus on what the solution is. Right. And again, the interval matters, but since I wrote everything in black, which I shouldn't have, I wanted you to put your attention on what the solution is. Okay? So what that means is we can solve any second order ODE that's linear. Doesn't necessarily have to have constant coefficients, as long as we have the complementary solution and as long as P, Q, and G are continuous on a common interval where the complementary solution is the general solution of the homogeneous case. Right? So what I'm going to do is in the next video, I'll write this out as a theorem, right? So we went through all the hard work of deriving this, right? So we don't ever have to do this again. All you have to remember are the assumptions, right? Basically that YC is the complementary solution, P, Q, and G are continuous, and that's all we need. So that's going to come in the next video.